Welcome to videos on linear integrated circuits. So in this ninth part of that, we shall see R2R current mode digital terminal converter. So this is circuit diagram for current mode R2R ladder network. So as you can see here now, the main difference is the current is passed through this inverting amplifier. So the output voltage is given by minus I0 into RF. We can see the current will flow to the inverting terminal or to the non-inverting terminal depending on the switch bit position, whether it is B0 or whether B1 is 0 or 1. So as you can see in all the switches, the switch will be either connected to the non-inverting terminal or the inverting terminal depending on the bit position 0 or 1. The bit position is 0, all the switches will be connected to non-inverting terminal. If the switch position, the bit value is 1, it will be connected to the inverting terminal. So meaning this position will be connected to the inverting terminal of your op-amp. If the bit is 1, if it is 0, it will be connected to the non-inverting terminal. Meaning to say, either we are going to have the I0 current or I0 bar current depending on the condition of the switch, whether it is 0 or 1. And it is interesting to see at any point of time the sum of current, that is I0 and I0 bar, will be always the same, because the switch will be either connected to the inverting terminal position or the non-inverting terminal position depending on the bit value. Meaning to say, this I0 plus I0 bar is always equal to 1 minus 2 power minus n into V reference with the R, regardless of the combination of the input. And the input code, that is I0 bar, is said to be complementary that of I0. If I0 is increasing, I0 bar is reducing. Suppose if your I0 is reducing, I0 bar will be actually increasing. So this is why it is called as complementary. Let us see the working of this current mode R2R ladder network. As you can see here, so we have different nodes V1, V2, V3, Vn minus 1 and Vn. So it is clearly evident that voltage at node V1 happens to be reference. Because of this R2R ladder network, the voltage at V2 happens to be V1 by 2, that is V reference by 2. The voltage at, because since it is, so let me just, the voltage at second node happens to be V reference by 2. Here it was V reference, now it is V reference by 2. The voltage at the third node happens to be, that is V3 happens to be V reference by 4. Likewise, the voltage is keep reducing. So what is the help of having these voltages at V1, V2, V3 all divided by half of the previous node? As you can see now, V3 is half of V2, V4 is half of V3. So we can see we have a binary rate of the voltage at different nodes is reducing by 2 power 1 time. And it is necessary to note that the value of I0 is always equal to I01, I02, I03, I04, I05, like up to In. So these are all the different currents which are flowing through. So this is possible when that bit position is 1. So this is I0 is equal to, when the bit is 1, it is I01, when the bit is 2, it is I02. Likewise, this I0 will be getting the current I1, I2, I3. So this we can write it as I1, I2, I3, or I01, I02, I02. Now what is actually I01 is, it's actually V1 by, so as you know that this is V1, V1 by 2R is this I01, this I2, I02 is V2 by, this is voltage V2, V2 by 2R. So this current I3 or I03 is V3 by 2R. So likewise, the current that is flowing through this inverting terminal is given by, in terms of V reference by 2R, V reference by 4R, V reference by 8R, and V reference by to power n. So because we are simply replacing this v1 by v reference, v2 by v reference by 2, v3 by v reference by 4. So that's what we saw in the previous slide. We had this as v reference by 2 and v reference by 4. So this 2 will become 4r and this 4 will become 8r because you are dividing it by 2r. Because all the currents are obtained by dividing that nodal voltage by 2r, nodal voltage by 2r, nodal voltage by 2r. So that's what we are having here. So we know that the output voltage V0 is given by the current flowing through this RF, that is minus I0 into RF. So it is now minus RF into, we are writing the expression for I0 over here. So taking out R constant, which is R as common factor in all the terminals, we can write the output voltage as minus RF V reference divided by R into V1 into 2 to the power minus 1 plus V2 into 2 to the power minus 2 plus so and so. As you can see now, this is exactly the expression what we are dealt in the initial DAC series of videos. The output voltage now purely depends on the combination of the input voltage, input pattern. V1 happens to be MSB and Vn happens to be the LSB value. So let us see how do we realize this particular DAC. See now, so we have talked about this switch SW1, SW2, SW3, but how does these switches are actually implemented in an IC? So we can carefully see here. So we are having transistor M1 to M7. So this M1 to M7 along with this M8 and M9 will act like diverting the current I to I0. Whether this whatever current I1, I2, I3 we have, how does that current will be going to the inverting terminal or the non-inverting terminal. Now this is I0, this is I0 bar. Now let us take an example. If you can carefully observe, this M1 is a PMOS, this M2 is a NMOS IC. So which all ICs which are there in the pull down network happens to be NMOS. This M2, M5, M7 are the NMOS ICs, whereas M1, M3, M4, M6 are all PMOS ICs. We know that for a NMOS IC, if you give a positive gate to source voltage, it turns on. Once it turns on, current flows through that and voltage across that MOSFET happens to be very small. Whereas for a PMOS, you can see this is source and this is drain, this is gate and this is drain. When the gate to source voltage is negative, the PMOSFET turns on, whereas for the NMOSFET, the gate to source voltage should be positive. Let us see what happens when the logic input is. So, okay, this is how an actual DAC IC looks like. We'll come to the detailed working of this MOS switch in the coming slides. Now, depending on the switch condition, depending on the input logic condition, that is 0 or 1. If it is 0, the current has to flow through I0 bar. If the logic is 1, the current has to flow through I0. We shall see the working of this switch in the coming slides. Now this is how a DAC IC looks like. So this is going to have a R2R ladder network which is connected in this fashion, and we are going to have switches being implemented by this MOSFETs. Now let us consider the operation of the switch. Now this is again we are again looking at the same switch. Assume that if the input logic is 0. So if the input logic is 0, as you can see, I am writing there is a 0 input here. The 0 input is there because now you can see the gate to source voltage is 0. So this will be an off condition. Now you can see this is 0, whereas this is VDD. If you actually find gate to source voltage, now gate is 0, this is 5 volts. So it is 0 minus 5 happens to be minus 5 volts. Since we have VGS which is negative for a PMOS, so this MOSFET M1 turns on. So when the logic input is 0, this is off, this is on. When this is on, we're going to have the entire voltage coming to this, flowing through source drain, and we're going to get a high voltage at this point. So output of this will be now high. As you can see now, the input is 0, the output is high. So we call the combination of a PMOS and a NMOS connected in this fashion acts like an inverter. Since the input is 0, output is high. So this is like the inverter. This is the basic circuit of an inverter. When the input logic is 0, M2 is off, M1 is on. So I have the output of the first inverter as high. Since this is high, so this M5 is on, M4 is off. Since M5 is on, this is off. The voltage at this inverter happens to be now low. So since this is low, this is connected to this M3. So this low will make this transistor also on, so that you'll be still having a high voltage here. Once this is low, so as you can see, this is low applied to this M7. So M7 will also be off. You can see now this is off. We have this is out of condition. This is on. Once this is on, we can see now this will become high. Once this is high, so we shall see what happens to. Now see now, since this is high, this current is now, this MOSFET M8 is on. When M8 is on, whatever the current that is coming from one of the node will flow through M8 and it will go to I0 bar. Carefully see, we are looking for a logic of 0. When logic is 0, actually the current has to go to I0 bar. That's what is happening here. When this logic input is 0, we are having the combination of these switching on, switching off, and finally M8 is turned on. When M8 is turned on, this current will certainly flow through. Just you can see, when this is 0, we are having ineffectively M8 is on. When M8 is on, this current I of K is flowing through. You can see now the current is actually flowing through I0 bar. Because this is off, the current won't flow through this M7, it won't go to I0. Let us see how does the current flow through I0 when the logic is 1. So I'm considering the logic of 1 here. So when the logic is 1, so as per our assumption, the current should flow through I0. So let us see what happens when the logic is 1 here. Keep observing the switch position, switch condition, MOSFET conditions. So when the input logic is 1, because this is 1 means VDD, so M2 turns on. This is off, this is on. Why this is on means because we have applied sufficient gate to source voltage. This is on, this is off. When this is on, this is off. The logic input, which is the input logic which was 0, will actually going to give a low at the output because it's an inverter. You can see since this is low. Since this is low, so this is off, M4 will be on. When M4 is on, we want to have the output as high here. The output voltage of the second inverter becomes high. Once this becomes high, this M3 will continues to be in off condition. And since this inverter is connected to the inverter output is connected to the input of the third inverter, this high will make M7 on and M6 is off. Since this is on here, we're going to have the voltage at the third inverter output happens to be 0. So you can see now this is 0, meaning M8 is getting 0, whereas M9 is getting high. So since M9 is getting high and M8 is getting low, M9 is on. So M9 is on, this is off. So naturally the current will flow through I0. You can see now the current that is flowing through IK will be directed to I0. Meaning in the previous slides we have said that when bit is 0, current will flow through I0 bar. When the bit is 1, the current will flow through I0. So that's what is That's how it will be done using these switches, and current is directed to either I0 or I0 bar.